Good morning, everyone, and welcome to re:Invent. Watching the Paris Olympics this year was an incredible experience for me. You had millions of viewers tuning in from across the globe, expecting a flawless, real-time viewing experience. But how are you able to deliver that level of performance on such a global scale? So in this session, we're going to talk about how Amazon CloudFront played a pivotal role in achieving that. Whether you're dealing with live streams, dynamic content, or static websites, high availability, security, and latency in milliseconds are non-negotiable requirements in today's world. I am Sagar Desarda. I lead our TAM organization for generative AI ISVs, and I'm also an Americas leader in our Ad Specialist team. With me is Sean. He runs our CloudFront product team, and we have a very special guest with us, Srini. He's VP of Engineering at Warner Brothers, one of our customers. Thank you. So our agenda for today is I'll do a quick overview on CloudFront and walk you through the journey of an HTTP request from CloudFront's lens. So the journey starts when the end user makes an HTTP request. So we'll look at how CloudFront DNS and Route 53 work together to minimize the latency, routing the traffic to the nearest edge. Once the request is at the edge location, I'll talk about CloudFront's caching architecture along with the policies for managing the cache content. Next, I'll walk you through how CloudFront functions and Lambda at edge bring powerful serverless compute right to the edge. And as the HTTP request travels through the CloudFront platform, we make real-time routing decisions to ensure that it stays fast, even as the traffic conditions change. And if the request is not cached, we quickly figure out what's the best route to the origin. So Sean will explain various ways you can connect CloudFront to your origin. I will mainly focus on the web performance part, and then Srini will share his insights on running large-scale media events like Olympics on CloudFront. So Amazon CloudFront is a globally distributed CDN, or content delivery network. It's designed to deliver content with low latency, high transfer speeds, and optimal reliability. At the core, we have 700 POPs across more than 50 countries that cache copies of your content closer to the end users. CloudFront speeds up the distribution of your content by routing each user request through the AWS backbone network to the edge location that can best serve your content. This, combined with CloudFront directly prioritizing peering with several ISPs, reduces the distance the data has to travel, thus enhancing performance. Last year, we took things a step further by launching a new kind of POPs, embedded POPs. So CloudFront embedded POPs are deployed directly in the end user's ISP networks. And that's unlike the CloudFront POPs that are deployed within the AWS network. Embedded POPs are purpose-built to deliver large-scale cacheable content at high scale, such as your video streams. It could be your game downloads, whereas CloudFront POPs are designed to deliver a variety of workloads. It could be your static, cacheable, or even dynamic content. And I'll begin with an overview of our standard CloudFront architecture, and then I'll talk about this towards the end. So this is where the journey of the HTTP request begins, with a DNS resolution. The faster it resolves, the quicker the browser can start fetching the content. So as the end user makes the request, it starts by going from the browser to the end user's ISP DNS server. This ISP's DNS is a recursive resolver. So it begins by locating the name servers. First, it'll do the top-level domain, like .com, and then it'll look at the specific domain, such as tntsports.com in this case. Once it identifies the name server, which is Route 53 in this case, Route 53 will pass that request to CloudFront DNS by translating tntsports.com into the long CloudFront.net hostname. From there, CloudFront DNS will determine the best edge IP to serve the content. It then returns that IP address, which is sent downstream to complete the request. So in 2019, we spoke about CloudFront DNS in detail. So check out the video behind the QR. But here's a quick overview on our approach. Our request routing happens on the DNS layer, but we go beyond a simple geolocation match. We collect performance data from every network to every CloudFront POP. We monitor server health. We look at network capacity, network conditions in real time to avoid congested routes. So we factor in all these values to determine the most optimal IP by routing around congestion, even across ISPs. In the last 5 years, we've introduced several enhancements to CloudFront DNS that I'm excited to talk to y'all today about. Starting with availability. CloudFront's DNS servers serves as the gateway to CloudFront CDN, making it the critical first point of contact for ensuring availability. To mitigate the impact of network isolation events at the edge and seamlessly scale with increasing DNS traffic, we've expanded our DNS fleet to include AWS regions, complementing our existing edge locations. What it means is we are now hosting CloudFront DNS in edge POPs, but also outside of edge POPs in AWS regions. And this is great because if an issue arises with an edge POP, or even an AWS region for that matter, other AWS regions can continue handling DNS requests, minimizing the impact on availability. This has given CloudFront DNS a much wider geographic footprint, which has led to a reduction in the DNS query latency by up to 30%. This means your CloudFront-powered applications on us experience faster DNS resolution, leading to quicker page loads and a more responsive user experience. We run health checks at both network and application layer, which provides early indicators of availability issues, which stem from individual POP disruptions, could be any issues with ISPs, or even subtle gray failures that we might see on our network. To complement this, our platform integrates custom monitoring mechanisms along with third-party DNS monitoring solutions. And then our internal routing algorithm, it aggregates insights from all these diverse sources that enables us to proactively reroute the traffic, ensuring uninterrupted availability for your applications. All critical CloudFront DNS components are now deployed multi-region, like sharing the POP capacity matrix, the handoff that happened between Route 53 and CloudFront DNS. Also, when you update your CloudFront configuration, our multi-region setup now actively polls for these changes in real time to ensure that your changes are quickly synchronized and applied. Our goal is to ensure that you never have to face issues like those in December 2021 when our customers were not able to make updates to CloudFront distribution during the US East 1 event that we had. Next is performance. So imagine you have a massive map, but instead of roads and cities, it's filled with servers, links, client load, network layouts, server hub data. And that is what CloudFront's routing algorithm uses. It's a complex routing table that responds to DNS requests. It's constantly adjusting to all these factors to find the best path for every request. Over the years, as CloudFront's traffic has increased, the routing table has become even more complex. Egress link congestion occurs when the outgoing network connection from a data center becomes overloaded due to high data traffic. With CloudFront's traffic growing rapidly, we needed a smarter and a faster way to handle these real-time changes without running into issues like egress link congestion or packet losses. To tackle this, we rethought our algorithm to make it more adaptive and responsive. So we categorize the data it processes in two different groups. The first one is the infrequently changing ones, like your end-user network topology that does not change too often. The second one is the frequently changing inputs, like the customer traffic, the health of the POPs, the capacity of our POPs, and so on. This redesign allows us to adjust faster and keep the performance high, even as the traffic demands increase. This has been crucial for us to maintain top performance even during major events that we've done, like Olympics or Thursday night football. With the resolver-based DNS routing, we've noticed that it always does not show us the true location of the client IP behind the DNS. And this can sometimes lead to suboptimal routing if the client and the DNS are too far apart. To address this, we now use eDNS client subnet along with latency-based and capacity-managed routing. So in my example here, my end user is in Mexico, but the DNS resolver is in Florida. Previously, this would have meant that the end user would have been connected to an edge location in Florida. Now, if the end user's ISP is configured with eDNS 0, the end user's location gets passed on to CloudFront DNS, and the user is connected to the CloudFront POP in Mexico. Given AWS's global scale, we've started partnering with major ISPs in US and worldwide to direct traffic through eDNS 0. In some cases, up to 100% of the traffic from specific ISPs now uses this improved routing method with us. So talking about recent enhancements, I'm excited to talk about this one. So when you use CloudFront, your end users connect through one of thousands of CDN IP addresses, and these IPs can change based on the end user's location. And this usually works fine, but this is not ideal for certain SaaS scenarios. Like enterprises partnering with network carriers, they might need to have a way to identify CDN traffic, to offer data exemptions or special pricing. Some of your partners might need CDN IP addresses to include in their outbound firewall rules. And managing that with thousands of rotating CDN IPs can be a challenge. So 2 weeks back, CloudFront rolled out support for Anycast IP addresses. So now, if you set up your CloudFront distribution with this feature, you get a set of 21 dedicated Anycast IPs. So when the request comes in, as you see here, it's routed by a BGP to the entry POP. If we identify a better POP to handle the request, the entry POP announces the routes for the Anycast IP addresses. And the response is then served from the closest POP back to the end user. So after the DNS response, my HTTP request is now in flight to land at the CloudFront edge location. One thing that we do know at AWS is security is a fundamental value proposition to our customers and for us. Over the years, CloudFront team has built or integrated a series of protection mechanisms. So we have AWS Shield systems. They scrub all the inbound traffic. They perform deep packet inspection to mitigate large DDoS events at the AWS region level. And this is transparent to you all, and this happens even before the request will even reach CloudFront. Then we have AWS WAF, Web Application Firewall, to protect your applications from application layer attacks and further reduce your attack surface. Over the past several years, application layers have become increasingly sophisticated. Bad actors are targeting vulnerabilities at the application layer with threats like DDoS attacks or OS top 10 exploits. They are all on the rise. So this surge in attack complexity highlighted the need for having a more robust and layered security solution for us to protect your applications against these evolving threats. So in response to this threats landscape, our CloudFront team developed a DDoS detection engine designed to automatically mitigate Layer 7 DDoS and flash share attacks directly at the CDN level. This offers a new level of security to our customers' data, and it ensures performance continuity. This is not meant to replace your AWS WAF. That's still going to have your application-specific rules. But think of this more as a tiered or a layered security framework on AWS. So to explain that, I'll walk you through the architecture, like what's inside the CloudFront POP, focusing on how the content is managed across our 3 cache tiers inside the POP, L1, L2, and L3. So when the HTTP request hits the POP, it first goes to a load balancer. And here we use ECMP routing to evenly distribute the traffic or evenly distribute the TCP connections across all the L1 servers. And the L1 server sits just behind the load balancer. So it's highly scalable. It allows us to host as many servers as we want at this level. Once the request reaches L1, the TCP connection is terminated, and the TLS session is now established. At this point, our DDoS detection engine is embedded on every L1 server that comes into play here. As the POP processes the responses back to the end user, the engine is actively scanning the traffic. It uses advanced techniques like anomaly detection, request fingerprinting, and does signature analysis to spot for any unusual patterns. We leverage a probabilistic data structure that spans across the entire CloudFront fleet, and it accesses the threat level, and then we assign DDoS confidence scores to these requests. And then based on this score, we'll decide what would be the appropriate mitigation strategy, and we'll block the request if needed. And the best part is this happens in line with the request, does not add any additional latency to your application. If the content is highly popular or hot, it's cached at the L1 tier, which holds a small amount of the most frequently accessed content. This allows us to serve popular content directly from the L1 cache. For content that's slightly less popular, it gets moved to L2 cache. So we use a consistent hashing algorithm here to make sure that every L1 server routes for the same object to the same L2 server. This ensures efficient storage utilization and increases cache offload by distributing the content more effectively for your applications. And now if CloudFront sees a request that we know that it's not in the cache, or if it's a no store or a post request, then L1 can go straight to the origin because it knows that L2 and L3 do not have that object. So here now, my request is at the edge location. So the next question is going to be, what rules do apply to this request? So this is where the edge POP will load the distribution config to see what's configured in it. For example, if you have configured your traffic to use TLS 1.3, HTTP 3, or set it up for WebSocket connections, those connections are applied here as the connections gets established at the edge. As your distribution config is loaded, at this point, I'm looking at the caching rules that you've set up, the compression settings, and whether you have any edge compute running on the POP. So I want to first talk about building a smart caching strategy. So from segmentation to multi-tiered caching to cache invalidation to proactive monitoring, each of these steps help you balance performance with content freshness. So starting with cache segmentation, for static assets, we use long-lived cache control headers and versioning for smooth updates. For dynamic content, we use cache policies and techniques like stale, while, revalidate to ensure faster responses even as the content is being validated with the origin. At first, it might seem like dynamic content cannot be cached, but just take a live video, for example. You might think it's non-cacheable because we always all need the latest segment. But the truth is, a lot of it actually can be cached. So with cache policies, you can create those caching rules by configuring the cache keys to include your query strings, request headers, cookies, and that can vary based on user-specific or request-specific data, ensuring that different variations of the dynamic content are cached appropriately. I recommend setting a higher TTL on the browser to reduce the number of requests that go to CloudFront. At the same time, set a slightly lower TTL on CloudFront for the same object. So that way, when the browser cache expires and triggers a new request, CloudFront would have already refreshed the content from the origin. And you achieve this by using a combination of cache control, maxage, and smaxage directives. By integrating cache purges in your build pipeline or CMS, you can trigger automatic invalidations whenever the content changes. And this ensures that users always get the most up-to-date version of your content without having to worry about stale cache hanging around. To optimize the cache performance, start by looking at CloudFront logs. They give you a clear view of the cache hit, cache miss ratio, which is a good starting point. but then also bring in external monitoring tools. They give you a more comprehensive look at your web page's performance. These tools can highlight areas that might go even beyond caching, like identifying page load times, where you can optimize the page load times, or like identifying the bottlenecks that might be slowing it down. So let's use this web page as an example. LCP measures the time it takes for the largest visible element of the on a web page to fully load and become visible to the user. It could be an image, it could be a video, or even a block of text. On this page, the large image here serves as the LCP element. So when I run a waterfall report on the web page, you can see that the browser does not start loading the image until 0.7 seconds. So what do? I run an experiment to add the preload tag in the source HTML of the web page. So as you can see, the large image loads at 1.6 seconds in my experiment on the left, versus it takes 2.2 seconds in the original run on the right. So to wrap it up, if your LCP is an image, consider preloading it. It's a simple step that can really help you boost performance. So with the LCP image preloaded, we've reduced the time to render on the web page. As you've configured compression in your cache policies, it further reduces the size of the objects that are then served downstream. When it comes to compression, I want to talk about fonts for a moment. Fonts can make up a big part of your web page's initial load, so having a compression strategy is key for performance. Here are my 2 quick takeaways on that. Go with the WAF2 fonts. They are broadly compressed, so which is much more efficient. By comparison, the WAF fonts, the version 1, is gzip encoded. The second is the data from the HTTP archive shows that 6 to 8% of the websites still apply gzip compression to the WAF2 fonts. Do not double compress. It only adds to the CPU load on the browser, and it just slows down your website, which is not needed. So now we've squished our assets down to size. Let's dive into edge compute, where you can process the requests closer to the end users to further reduce the latency. So you can run CloudFront functions on the edge POP. They are purpose-built for lightweight compute tasks that are designed to execute in just milliseconds. CloudFront functions execute JavaScript code natively at CloudFront's edge locations, and they can instantly scale to handle millions of requests per second. And our customers don't have to worry about burst or throttling limits. It has its own serverless scripting platform, and it allows you to use lightweight JavaScript code. And then we have CloudFront Key Value Store, or KVS. It's a global low-latency data store that integrates with CloudFront functions. So with KVS, you can actually now decouple the function code and the function data, and that enables you to manage them independently. And this simplifies your function code, and it makes it easy for you to update the data without feeling the need to keep deploying those code changes for function updates. Of the many use cases that our customers use CloudFront functions for, I'm going to talk about A/B tests, or running A/B tests. So it's common to run quick experiments to test out new features, layouts, measure conversions, gauge user engagement, and then depending upon the results that we see, we'll either scrap the idea or we'll adopt it in production. You can now run your entire experimentation framework on CloudFront functions. So in the diagram here, the experiment randomly assigns the user to an experiment variant and creates a session cookie to keep them consistent in that experience. As you look to serve multiple variants of the page from different origins, until a month back, you would have to write another function in Lambda Edge, and that would manage your origin routing. You can actually now do that within CloudFront functions. You can dynamically switch your origins, you can streamline your origin rewrites, and run your traffic routing on CloudFront functions. This approach also helps you further reduce the latency because you now have the compute running right at the edge POP. You can then store origin IDs in key value store and then use that data to dynamically construct the origin host name within the CloudFront functions. And this is particularly useful if you're running frequent experiments, spinning up, tearing down origins, since this avoids constant CloudFront config updates. Instead, your CI/CD pipeline can just simply deploy or update key value store, allowing for seamless redirection to the new origins as your experiments evolve. So as the HTTP request journeys from the edge POP to the regional edge cache, or the REC, it's assigned the most optimal REC based on the latency matrix. Each REC has a multi-AZ architecture, which enhances availability and resiliency. If the assigned REC encounters issues, we have a fallback option to switch to an alternate REC to maintain performance. The CloudFront platform also features built-in monitoring that tracks critical metrics such as request latency, connection times, request volumes, and such. Then we have our own custom monitoring built that sends HTTP requests into our platform with varying patterns, different HTTP methods, different object sizes, and such. By analyzing all of this data holistically, we have the ability to perform traffic engineering that enables us to reroute the request from the edge POP to a different REC when necessary. Lambda@Edge is our other serverless function that runs on the REC. While CloudFront functions are perfect for quick, lightweight tasks like header manipulation, Lambda@Edge steps it up a bit by allowing for longer execution times and handling more complex and resource-intensive workloads. It's ideal when you need a little bit more power and flexibility in your edge computing, and Sean's going to talk about this. As the HTTP request journeys from the REC to Origin Shield, there's an additional caching layer that further reduces the load on the origin. This setup ensures that only one request per unique asset is forwarded to the origin, minimizing the latency and optimizing cache hit ratios. Towards the end, Srini is going to talk about why Warner Brothers have Origin Shield configured and what it does. So next up, Sean will walk us through the final leg of the HTTP request journey.
All right, so your request is at the REC now. So what happens? This is where CloudFront retrieves the content from where your application is hosted, from the origin. So now we're inside the AWS network, and there are a lot of things that go into making sure CloudFront can successfully connect to your origin. We'll dive into 4 key concepts here: CloudFront origin groups, origin access control, or OAC, Lambda@Edge, and VPC origins. First, let's talk about origin groups. Sagar talked about ways that the CloudFront Edge maintains high availability in order to serve your content that it has cached. But what about the availability of your origin itself? Let's say that you're running live video streaming, and where minutes or even seconds of downtime or interruption would be highly noticeable to your viewers. One of the things you can do with your origin behind CloudFront is to run 2 parallel origins, 2 different origins for redundancy. So now, if one of your origins is overloaded or unreachable, you have a backup. So CloudFront performs failover from one origin to the other, from your primary to your standby, using HTTP-based health checks. Customers tend to really like this because of its near instantaneous failover decisions. Here you can see setting up 2 origins, and by checking the health of the primary server in real time through observing the HTTP status code that's returned from each request, if the primary server returns error codes or is completely unreachable, CloudFront will immediately switch over to the backup origin. You can configure the various HTTP error codes that you want to consider as failed, so 4XX or 5XX errors. Now let's talk about cases where your origin is Amazon S3. So S3 is great for hosting static content like static websites, videos, and using CloudFront then to deliver them to viewers. But how do you prevent viewers or bad actors even from directly retrieving the content from your S3 bucket? That would bypass your security controls, user authentication, and so on. Origin Access Control, or OAC, is the answer here. If you're using S3 as your origin, you really should make sure to have OAC configured. Once you have OAC configured on S3, no one can access S3 directly to retrieve that content. It can only be accessed from the public internet via CloudFront. So with Origin Access Control, the S3 bucket that you use as your CloudFront origin is protected using signatures on the requests and access control policies on the bucket. So CloudFront signs each request, and then the access control policy that you apply to your S3 bucket determines whether each request should be authorized or denied. Now, with OAC, you get security best practices baked right in for you, such as short-term credentials, frequent credential rotations, and resource-based policies. Now let's talk about Lambda at Edge. So Lambda at Edge lets you manipulate requests on the way in and also responses on the way out from your origin. So a difference from CloudFront functions, Lambda at Edge lets you look at and modify the actual body of the request and the response. So this lets you do some more sophisticated operations, things that require more compute, maybe require or rely on third-party code or libraries, or maybe require calls over the network to APIs or to retrieve data from data stores. So some example use cases would include, for APIs, schema validation on the input side, and then on the output side, transforming or masking data. It could also include on-the-fly conversion of videos or image optimization using third-party libraries. So let's walk through the example architecture on this diagram. Let's say that I'm running a product catalog service for an e-commerce application. On the origin request, I need access to the request body in order to run some schema validation. So I can use Lambda at Edge to do that. Then, on the origin response, I can invoke libraries to optimize product images or other media for different types of client devices, mobile, desktop, and so on. Next, I'm excited to share a new capability that CloudFront just launched as of a few days ago, VPC Origins. This is a new feature that lets you deliver content from applications hosted in private subnets in your VPC without any public connectivity to your VPC at all. We talked about Origin Access Control as the way to secure your S3 bucket, to lock it down from the public internet. VPC Origins is similar, but for securing your dynamic origins. So with this release, you can keep your application load balancers, network load balancers, EC2 instances in a private subnet that is accessible only through your CloudFront distribution. CloudFront does this by establishing a network tunnel from the CloudFront edge directly into your VPC, bypassing the public internet altogether. So this simplifies your origin connectivity. It saves you from having to provision public IPv4 addresses for your origin. And it reduces the security blast radius of your applications by preventing these origins from being reachable through any other way than your CloudFront distribution. So we've talked about ways to configure your origin and ways to lock it down from the public internet. Now, of course, you need to have an origin. That's where your content comes from. But your customers will get the fastest performance, and you'll also be able to run your applications with the lowest need to scale up your origin if you can minimize the number of requests or round trips between the edge and your origin. So CloudFront does several things automatically to optimize for the fewest and fastest round trips to your origin. We'll talk about a few of them here. Request collapsing is the first one. So this is great for things like live video streaming use cases. Thursday Night Football on Amazon Prime Video is a great example of this. So you have a lot of concurrent viewers from many locations requesting new objects that aren't in the cache yet, specifically the latest video segment. So CloudFront will recognize at the edge that all of these users are basically asking for the same piece of content at more or less the same time. And so CloudFront will collapse all of those requests into a single origin fetch. So CloudFront will serve the same cached file to all of the clients that are requesting it. Even if it's not yet in the cache, CloudFront will just consolidate that down to a single request. And this request collapsing happens at multiple layers in the CloudFront system, at the edge POPs, and then also between the regional edge cache, or REC, and your origin. Next is byte streaming. So even when there's a cache miss, CloudFront will still try to get the best possible experience for your viewers. So we do this by, instead of waiting for the whole object to download from your origin into the cache and then serving that file from the cache, what CloudFront will do is start to send that file on to the viewer as soon as the first byte from the origin reaches CloudFront. So CloudFront will literally stream that object back to the viewer. So this way, you don't incur a big latency penalty on that cache miss. Next, connection efficiency. So we're talking in this session about milliseconds in the life of an HTTP object or a request, and the time required to establish the TCP connection and perform that TLS handshake account for a large chunk of that time. So CloudFront tries to be efficient in the use of that handshake. And so once CloudFront has established the connection to the origin, CloudFront will try to keep that connection open for a few extra seconds in case another request comes in during that period to that same origin. So this makes future connections a lot faster because you don't have to reestablish that TCP connection and TLS handshake. Now, for Origin Shield, I'm going to take a pause here and hand off to Srini, who will talk about a great real-world use case.
Over the past year, Warner Brothers Discovery has delivered multiple high-profile events, such as the Olympics in EMEA, the UEFA Cup in Latin America, and the 2024 presidential elections. For any House of the Dragon fans here, we delivered that content as well. I'm sure you're wondering, wait, what does the House of the Dragon have to do with some of these high-profile live events? Think scale. When we drop a new episode of the House of the Dragon every week, we see millions of customers eagerly waiting to press the play button. And when they do, we see a thundering herd of requests hit our backend services, primarily the entitlement services and the URL vending services. Now, when this happens, and these customers stream the content for about 50 to 60 minutes, which is the duration of the episode, we start to see a steady increase in the number of concurrent viewers. This stresses our ad systems, our origin, and our POPs. So you might be wondering, wait, what makes the Olympics such a challenging experience? The Olympics adds another dimension to scalability. It's the scaling of concurrent events. When we run the Olympics, there are hundreds of events taking place at the same time. Now, each one could be as big as a House of the Dragon episode. The Olympics was run across 47 different countries in EMEA in 19 different languages. That's a lot of data flowing through our system. This requires a lot of bandwidth, especially the CDN ISP peering, and careful CDN load balancing to ensure there's no disruption to the end customer. On August 4th alone, we had 600 million minutes streamed. To put that in context, that's 1,141 years. Now, the 100 meters finals accounted for majority of the traffic and saw a surge in traffic 5 minutes prior to game start. Oh, and we did all this with absolutely no outages. So that's a testament to the hard work done by the Warner Brothers Discovery teams, as well as our partners, including AWS, to deliver at this level of scale and resiliency. Running high-profile events is challenging. They test almost every part of our system. I'm going to break these challenges into 4 main buckets. The first is security. Now, such high-profile events attract attention. And sometimes it's not the kind that you want. Unauthorized access impacts your revenue, and they impact your customer trust. Imagine paying for a subscription to watch your favorite show, only to find out that the same content is available for free on an illegal site. This can cause streaming platforms to lose customers. The next is quality. I have a question for the audience. How many of you have stopped streaming your session because of poor quality or excessive buffering? Exactly. Audiences expect high-quality audio and video. I'm talking 4K, HDR, Atmos, all across multiple devices with varying network conditions and absolutely no buffering. The third is scale. Now, I've already spoken about the 3 types of scale: the scaling of concurrent events, the scaling with concurrent users, and the scaling with stream starts. And the Olympics saw all of them. And now, imagine having to do all this with 100% availability, no glitches, no downtime, That's the level of reliability our audiences expect. Now, I've spoken about the 4 main challenges. Let's quickly take a look at how we solve this using CloudFront. But before going into the solution, let's take a quick look at this architecture. In this architecture, when the user streams a content, we have multiple CDNs in play, out of which CloudFront is one of those CDNs. This architecture is what we call the CDN sandwich architecture, where all data flows through CloudFront, which is the only CDN that is connected to the origin. This helps us with better cache offload, and it helps keep our origins running smoothly and efficiently. Now, let's talk about security. Course gives us the flexibility to publish our stream on multiple platforms. Having a tight course policies helps us prevent unauthorized access that is crucial for our business. During one of the major live events, we saw a surge in the number of unauthorized access because sites were embedding our stream in their applications. Now, this is a serious issue for 2 reasons. 1, it's a breach of security. And 2, it's a hidden cost to us. We end up footing the bill for the hackers. So to tackle this, we use CloudFront functions with tight course policies to prevent unauthorized access. Now, CloudFront natively also supports course, but we use CloudFront functions because it gives us the flexibility to customize it. Take a look at the GitHub link behind the QR code for the course implementation. During this Olympics, we saw a 77% increase in our subscription rate compared to the previous Olympics. With this growth in viewership, there's also a strong need to continue to protect our streams. We use CloudFront functions to validate our tokens to prevent unauthorized access to further beef up our security. Now, if I was running a 2-hour NBA game, say with 1 million customers streaming the content, I would see a total of 1.8 billion requests hitting our CloudFront function for the token validation. Each user would be making a request every 4 seconds, assuming that that's the segment duration for our stream. Now, if I decided to do this as an on-prem solution, I'm pretty sure Avi, my CTO, would be at my desk wondering why I gave him such a huge compute bill. With CloudFront functions, I'm able to do it with low cost, low latency, and high scale. The cost that you see here is the cost per user for the entire duration of the game. Let's talk about the 100 meters finals, one of the key moments of the Olympics. There were 1 million customers watching and obviously 1 billion requests hitting our backend systems. Now, while the recs do a great job of protecting our origin from the traffic, the reality is there's still a lot of requests that make its way to the origin. And what's more is that when 2 recs are making a request at the same time, they're most probably asking for the same object. This could pose to be an availability challenge for the origin. How did we solve this? We used an origin shield. So what I can do is I can configure the rec that's closest to my origin as an origin shield. So here's how it works. Multiple recs funnel their requests through the origin shield that is connected to the origin. This helps with better cache offload and reduces the number of requests that hit the origin. Now, since there are fewer number of requests hitting the origin, I need fewer number of connections. And since there's a persistent connection set up between the origin shield and the origin, the keep alives already exist. So I don't need to continue to create more connections, and that helps with the throughput. Now, if I take the same scenario, if I was running a 2-hour game with 1 million customers streaming, totaling to 1 billion requests, with a 4-segment duration, we noticed a 5% improvement in our cache offload when we used an origin shield. So if you are hosting your own website, here are the results. We saw a 99% cache offload for on-demand and a 95% cache offload for live content. So if you are hosting your own website or you are running your own e-commerce or streaming platform, I highly recommend that you use an origin shield to protect your origin. With that, I'm going to hand it off to Sagar.
So up to this point, we focused on optimizing performance at the edge. And then Sean covered how do you optimize from CloudFront to origin. However, there's still a challenge with last mile latency, that segment between the end user and CloudFront. During high traffic events like Olympics or UEFA, we've observed that some of the cities who have smaller bandwidth pipes, they experience congestion, and that impacts the viewer experience. So to address this, I spoke earlier about how we've built embedded POPs for large-scale cacheable traffic, and we've started deploying them directly within the end user's ISP. So this brings the CloudFront CDN much closer to the viewers, delivering the content directly from the ISP for a much faster experience. Ahead of the UEFA Cup this year, we worked closely with Srini's team to onboard embedded POPs into their application, which reduced the rebuffering rates that their viewers would see. Across all of our customer base who use embedded POPs today, we've seen up to 20% improvement in first byte latency compared to the requests that are directly served from CloudFront POPs. Embedded POPs are an opt-in capability. And the best part is integrating embedded POPs into your application comes at no additional cost. So I would say just reach out to your account team and see if embedded POPs are a good fit for your workloads. There are two ways to integrate embedded POPs into your application. The first is using HTTP redirects. So here, you do not need to make any changes to your application. We make a change on the back end. And when the request hits the CloudFront, the Edge POP issues a redirect with a different host name. Browsers handle redirects seamlessly, so that's not an issue. However, if your application has your viewers using, say, streaming devices or gaming consoles, you just want to make sure that they are supporting the redirects. So as the redirect happens, a new request is sent to the CloudFront POP with the new, or sent to CloudFront with the new host name. At this point, the end user connects to the embedded POP as one is available within their ISP. This does introduce an additional TLS session, but most devices and browsers today reuse the connection. So from our experience, it's been that this overhead is minimal. Many of our gaming customers, as an example, prefer this approach. The initial redirect is quick, and then since the game downloads are typically lengthy, the impact of a single redirect is negligible over the total download time. Another option is integrating the CloudFront SDK directly into your URL vending machine, the system that provides authenticated URLs to your end users. So here's how it works. The client requests the manifests from your URL vending machine, which generates secure links for streaming the content. Our SDK is directly integrated into your vending service. When the client requests the manifest, they are able to start streaming from CloudFront. There are two benefits to this approach. The first one is, with the SDK, we pass on the client subnet information to CloudFront DNS, and that allows for more efficient and granular routing, even in cases where the client's ISP does not support eDNS 0. Since the entire request stays on the same host name, you avoid that extra overhead of establishing an additional TLS session. Our live streaming customers prefer this approach to maximize every incremental millisecond that they can save. So while embedded POPs are a key part of optimizing the routing and reducing the latency, they only address a subset of the challenges that arise in live streaming. Live streaming is not just about getting the content to the users faster. There's much more at play. For example, even with the most optimal routing that you can possibly have, even with your regional performance improvements, live streaming still faces network variability challenges. You will still see scalability challenges, particularly for high traffic events that we've been talking about. Users may experience fluctuations in bandwidth for maintaining high quality streaming across diverse devices or across multiple regions, and that can be difficult. So I'm going to ask Sean to come back up and talk about something really cool that his team has built and see us through the end.
So there's one more release that I'm excited to share with you today, and that is Media Quality Aware Resiliency, or MQAR. MQAR is ideal for when you want to maintain the highest resiliency for streaming high-stakes live video, sporting events, or concerts. Previously, I've talked about how CloudFront can fail over from a primary to a backup stream if one of those streams becomes completely unavailable, using origin groups. But availability isn't the only consideration. Quality of that video stream is also equally important. So take, for example, that a video stream may be available but have degraded quality. Video frames are dropping out, the audio quality may be poor. Traditionally, you would have to have a live human operator, what we call eyes on glass, to monitor the video quality experience and then manually trigger a failover from your primary to your backup video source. Now that obviously takes many seconds to happen, during which time your viewers are going to have a degraded experience. But now we've launched Media Quality Aware Resiliency, again, MQAR. This is an integration between Elemental Media Services and CloudFront, and it consumes a dynamically computed quality score for each of your two redundant video streams. This provides then near instantaneous cross-region selection of origin based on this dynamically generated video score. This basically automates the eyes on glass and will cause a failover to happen much more quickly. Nope. So we'll talk about the architecture on this slide. So let's again say that you're streaming a live video. You will have two redundant AWS Elemental Live video sources. Each of those will then be plumbed into two Elemental Media video processing pipelines. And these exist then in two different AWS regions for redundancy. Then at each stage in this video processing pipeline, from ingest through transcoding through packaging and origination, the quality as well as availability of those two input signals is compared. And automatically at each stage, then that quality is used to determine which of those input signals to use. The two streams across regions are then time synced so that if there is a failover from one to the other, your viewers will not notice a hiccup in that video stream. Then Amazon CloudFront will independently at each stage in the CloudFront system, so the origin shield, regional edge cache, and edge location, determine which of those two redundant video pipelines to actually consume from based on which one has the highest quality score at that given moment. So to recap, we've covered a lot of different ground in this session. We started with architecture, so how CloudFront is designed to deliver high availability and low latency for all types of content, with more than 700 POPs to get content closer to your end users. Content is fetched from your origins over the AWS backbone network, so avoiding congestion on the public internet. And we're paired with major ISPs all over the world. Next, for a caching strategy, so you can use embedded POPs to get large files even closer to your viewers inside the ISP networks. You can make use of cache policies and origin shield to maximize what's cached for fastest site performance and minimum hits to your origin. We talked about compute at the edge. Two options: CloudFront Functions for lightweight request manipulation right at the CloudFront POP, and then Lambda at the edge for a robust serverless compute environment. Then for securing your origins, VPC Origins locks down connectivity to your VPC to just your CloudFront distribution, while Origin Access Control secures your S3 origins. Lastly, we talked about continuous innovation, so things like DNS latency reduction and availability enhancements. The new DDoS detection engine built right into the CloudFront Edge servers. And lastly, Anycast IP support for use cases that need fixed IP addresses. With that, we'd like to thank you for attending the talk. Please do complete the session survey in the mobile app. This helps us continue to improve our sessions year over year at reInvent. And again, on behalf of the presenters, thank you. We will be available just outside the room for any Q&A. Thanks so much.